Okay, hello everyone. My name is Jake Hanson, and I'm here to share some work that I've been doing with Steve Desch regarding disintegrating planets. And hopefully it's not too confusing that Owen's talk was about hydrodynamic escape from normal planets, and these are disintegrating planets, much lower mass regime, but still exhibiting hydrodynamic escape. And I think there is some overlap, but I haven't been able to think about the details of exactly how they overlap. So hopefully it doesn't confuse you. Hopefully it's enlightening to some of Owen's research. Okay, so why care about disintegrating planets at all? The reason that disintegrating planets are important is because it's one of the few ways that we can get simultaneous mass and composition constraints observationally about planets. The distribution of planet composition as a function of mass is ultimately what's going to constrain which planetary processes are possible. So things relevant for life, such as abiotic outgassing and tectonic activity, are going to be constrained by planetary composition. So we're going to need to have a handle on the distribution of composition if we want to constrain the abiotic signature. So in other words, how I'm viewing this problem is we're getting starlight passing through an atmosphere that we hope is from a planet teeming with life, and the spectral signatures of that life are imprinted in the spectrum. And we catch it with JWST, but we need to be able to separate that from an abiotic world that also has spectral signatures in its atmosphere, and that's going to depend on the compositions of the planets, or the distribution of composition. How you actually can get a composition is actually a very involved process. The first step is to understand how these planets are disintegrating, which is through Parker winds, which is a steady state mass loss, hydrodynamic mass loss. And then we're going to use the Parker wind formalism to constrain what properties are allowed. So the mere existence of a steady state Parker wind actually puts some constraints on what mass planet you can have, as well as the mean molecular weight for that planet's atmosphere. So this is different than other forms of escape that are not steady states. This project is all through the lens of steady state. And then once we have the mass, we can calculate the velocity structure of the wind. So ultimately, these winds are accelerated beyond the escape velocity of the planet. And so the velocity structure tells you when the wind will escape. And then we're also going to couple the velocity structure to a mineral condensation code. So that's really the unique portion of this project, is going to be coupling the hydrodynamic escape from a Parker wind to a condensation code that tells you how gas vapor condenses into dust. And that's ultimately what you'll want to compare to spectra from JWST. But unfortunately for you all, this project is just focused on the first portion of this project. So what can you learn about planets that are hydrodynamically losing mass via Parker winds? So a little bit more about disintegrating planets. You may be surprised to know that there's only 4 known disintegrating planetary systems, 3 around M stars and 1 around a white dwarf. Observations tell us that these planets are extremely low mass. There's upper limits on their masses. They're hot, rocky, and ultra-short orbits, so periods of order of 1 day. You can back out the mass loss rates from the transit depths, and people have calculated that it's about 1 Earth mass per gigayear mass loss rate. So for a low-mass, Mercury-mass planet, the mass loss rates are quite substantial. And the general thinking is just these planets are too hot to hold onto the material. So surface material is being vaporized. This is different than losing an atmosphere. And that vaporized material then forms an atmosphere, which is kicked off. As for how they're actually detected, there's 2 big telltale signs that you're looking at a disintegrating planet. The first is variable transit depths. So you can see this is a periodic signal, but it varies in depth. And the second is an asymmetric transit profile. So you can see the ingress is a much steeper gradient than the egress, and that's due to the diffuse portion of the tail taking a long time to exit the face of the star. So I've mentioned Parker winds a few times. A little bit of the historical context. They were originally developed by Eugene Parker to describe the solar wind. So it's the exact same physics from solar wind physics, but now we're applying them to exoplanets. So we're 40, 50 years, 60 years behind, but we're there now. And Cayman told me that if I put too many equations, he would personally kick me off the stage, but I slimmed it down, and these are the basics. All that you really need to know is that it's a force equation where gravity and pressure is trying to balance. If the right-hand side of that top equation is 0, that's hydrostatic equilibrium. If you allow for a non-zero acceleration, then you'll get the potential for a Parker wind. The only other pieces of information you need are a law for conservation of mass and an equation of state, which we assume a polytrope here. And then the result, we'll see how many is too many here. The result is that you get the wind velocity as a function of distance. So that's really what we're after. This dimensionless variable psi is velocity, and distance is the dimensionless variable c. And then we also have the Jeans parameter, which is a ratio of the gravitational potential energy to the thermal energy. And that kind of characterizes the likelihood of a planet to have this wind. So that was abstract. If we were to imagine putting Mercury in a radiation environment of 2100 Kelvin, we could ask ourselves what would happen to our beloved Mercury. And basically, you can see that winds can develop, and about 8 Mercury radii away, the wind would reach escape velocity. So Mercury would undergo mass loss. What you don't see in this plot that's very important is that the mean molecular weight of the atmosphere is incredibly fine-tuned for this plot. This is a 6 hydrogen mass atmosphere. If I try to do the same thing for 5 or 7, there's no Parker wind solution. And so the generalization of that is that there's 2 different regimes for Parker winds to, you have to operate between them. In the upper regime, so you can see this is planet mass and atmospheric mean molecular weight. In the upper regime, your planet is too massive or cold for your wind to overcome gravity. In the shaded regions, those are different temperatures that would have a Parker wind solution. So you can see for Mercury, if you knew the mass, then you could calculate there's a very small mean molecular weight that would allow for a steady state Parker wind to develop. And these are 4 different temperatures. And the lower regime is kind of the more subtle one. In this regime, you can think of it as too little mass for a wind, but I think it's easier to think of it as having too much thermal energy for winds to hold their shape. So a Parker wind is a subsonic to supersonic wind, and if you start your surface velocity supersonic, there's no solution that kind of keeps that structure propagating outward. Your equation blows up, and you basically don't have a wind. So that's not to say these planets can't lose mass. They probably are losing mass through non-steady state means, but there is a lower limit for steady state Parker winds. And so the implications of that are that these Parker winds are extremely fine-tuned. If you want to assume steady state mass loss, you have to be in a very small parameter space. What you would expect instead is for aperiodic or sporadic mass loss corresponding to brief periods of time in the Parker wind regime. And the process itself may be self-regulated or throttled. So you can imagine building up an atmosphere, slowly heating your surface temperature until eventually you reach the point where you're in the steady state mass loss regime. All of a sudden you get these bulk ejection events, and then you cool down and get back to where you started originally. And so that's my tip of the hat towards the alien megastructure stars. Perhaps this is it. But I would like to share this quote with you from a BuzzFeed article that says, "No amount of extreme math so far has figured out what is going on with star named KIC 8462852. And I kind of laughed at that because I thought it sounds childish, and I thought, wait, that's basically exactly what it is. So anyways, a few applications of this. We can look at something like 55 Cancri E. You see it's a super Earth, very hot, 2000 Kelvin. The period is less than a day and high density. So it fits the bill for what a disintegrating planet should be. But if you plot the mass, of 55 Cancri E, you can see that there's absolutely no reasonable temperature. So the green line is 3000 Kelvin surface, the blue is 1300. You can see there's no solution that comes in contact with a mass of almost 10 Earth mass. It's just too massive of a planet. So if we try to lower the mass of the planet, so this is a 0.85 Earth mass planet, TRAPPIST-1b. This planet, if it were at 2000 Kelvin, it would have a solution for Parker winds, but the problem is that it's at 400 kelvins. This planet's just too cold. And ideally, I would like to show you something in the other regime of this too, a planet that's too small or too hot for a Parker wind. But the problem is that if you get planets that are that low of mass, we have no way of detecting them to begin with unless they're disintegrating. So basically, I have 2 examples for planets that are too massive or too cold, but no examples for too hot or too light because they're impossible to detect. But we do have these known disintegrating planets. These are low mass planets that exhibit almost steady state mass loss. And I say almost because each period they are continuously losing mass, but those small variations in transit depth show that it's not perfectly it's not a perfectly steady state system. So this plot now, these colored regions show the solution space for those different planets. So I said there were 4, but 2 of them have the same effective temperature. So here I'm taking the surface temperature to be the effective temperature. And you can see this is the allowed solution space. And even without knowing the molecular weight of these planets' atmosphere, you can put a constraint on their mass just by assuming that the mean molecular weight of the atmosphere is somewhere less than 60. If you were to get better constraints on the mean molecular weights of this atmosphere, you could put very tight constraints on the allowed mass for these planets. But without the mean molecular weight constraint, you can still constrain them to be somewhere between 10 to the negative 3 Earth mass and 1 Earth mass. And so the upper limit obviously is not that surprising. You need a very small mass planet to be able to eject a wind. But the lower limit is somewhat counterintuitive. And that's basically because I think the wind can't hold its shape. So anyways, the part that would be nice to tell you more about is the mineral condensation portion. So I can give you a small teaser for that. And basically, what you do is you assume your planetary parameters. So you assume your surface temperature and stoichiometric composition. And then you calculate the velocity profile of your wind. So your wind profile depends on your mass and surface temperature. And then you will compute 2 relevant timescales. The first is basically the timescale for gas to condense onto grains. And the second is the timescale for the wind to diffuse. If you set these 2 timescales equal, you can calculate what's called the freeze-out radius, which is defined as the point beyond which the wind is moving too fast for your particles to condense. And so that will be the final distance at which you're actively condensing minerals. And then what the plan is to iteratively condense from the surface out to this freeze-out radius and compute your mineral abundances, and then compare that to observed spectra. And in theory, you can go the other way, but obviously this isn't the portion that we've worked out in all the detail. So in summary, compositional constraints are very important because we're going to need them to put constraints on the abiotic signatures of planets. Disintegrating planets allow simultaneous mass and compositional constraints, which is very important. And the main results from this talk are that Parker winds are a very fine-tuned solution space. And aperiodic or throttled mass loss is probably more likely, where you pass in and out of this regime where you're capable of launching steady-state winds. And for the known planets, the mass constraints that we would put on them are somewhere between 10 to the negative 3 and 1 Earth mass. I'd just like to quickly thank Steve for his help, as well as my advisor Sarah Walker and the rest of our group for their help and advice. And if you have any questions, please email me at jake.hanson@asu.edu. Thank you.
Thanks, Jake. We have about 3 minutes for questions. Wanda?
Hi, Jake.
Hi, Wanda.
I am so sorry that I did not mention this previously. I see you almost every day. But you do realize that WD1145, the body that's orbiting it and what you're calling a disintegrating planet, is on a nearly circular orbit that passes through the white dwarf Roche radius at least twice during its orbit, right? That's why it's disintegrating. The Parker wind treatment that is applicable to the other planets, I don't think you should include the WD1145 rocky body with it.
Okay.
Okay.
I do, yeah. This treatment is just for a given surface temperature. And so I guess for the point of my argument, it's just a theoretical planet in that system would have this mass constraint. And that system's also complicated because there's the 6 different bodies. And so I would say the known disintegrating planets, the canonical ones that I'm thinking about are the 3 around the M stars.
Okay, good.
But yeah, the white dwarf is a little ratchet in this whole mess.
Right, no, but the reason why they're disintegrating is because it's passing through the Roche
Yeah,
radius.
and that is not the case for any of the other stars.
Okay.
Hi, Russell Dietrich, University of Washington. I was curious if the Parker wind, if the mass loss is ever really strong enough that you would get some change in the orbit of the planet. Do you see orbital decay? Would you expect orbital decay or anything like that?
Well, unfortunately, we don't have many of these systems, but there was the 2014 Rappaport et al. Paper. There seems to be a feedback mechanism where you see the depth of the transmit on a year average is getting shallower and shallower, and so that seems to imply that this planet is losing so much mass that the feedback from the mass loss has affected the mass of the planet itself in a way that dictates the mass loss again. So you can see a feedback process that the amount of mass it's losing is actively affecting its future mass loss. But that's the only case that has some sort of feedback mechanism.
Okay. Thanks.
All right, we have time for one more.
Hi, Bill Diamond from the SETI Institute. Just a question on the graph you had with the various light curve depths, because they did seem quite random, but they didn't seem to me to indicate a trend toward, suggesting continual mass loss. They seemed kind of all over the place.
Mm-hmm. So I think the point that I'm trying to make with the steady state mass loss of those planets is the fact that they're continuously losing mass puts them in and around the steady state regime. And so when I talk about the throttled or aperiodic mass loss, what I'm thinking of is planets that are far from the regime of losing mass via Parker winds, and then they enter the regime briefly only to lose an atmosphere and then go back to being far from the regime. And so I picture these planets as at least being close to the steady state regime, and the fact that they're variable, the depth of the transit is variable, I take to mean that obviously the surface temperature of those planets isn't fixed, and you do get fluctuations in the amount of mass you're actually losing, but they're very near that ideal solution where you're in an equilibrium.
Thanks, Jake.
Thank you.